Welcome to this explainer. Look, if you're a college instructor wanting to bring real hands-on scientific research into your classroom, you are exactly where you need to be. Today, we're unpacking a step-by-step, totally grounded blueprint for designing your MDH CUR syllabus. Whether you've been teaching for decades or you're just dipping your toes in and have very little prior CUR activity, this is your complete, practical how-to guide for building a really meaningful semester. Here's our roadmap. We'll start with understanding the MDH CURE, move into choosing your project theme, then structuring your syllabus flow, building with required modules, selecting optional modules, and wrap up with assessing the scientific process. Basically, we're taking a backwards design approach here. We'll be building your syllabus from the ground up, so you know exactly what outcomes you're targeting well before day one. Let's get right into it.
Section 1. Understanding the MDH CURE beyond the traditional laboratory course.
Okay, let's unpack this. If you look at shared syllabi from the MDH CURE community, the MCC, you'll notice right away that the strongest courses aren't your typical cookie-cutter biochemistry labs. An MDH CURE is actually an undergraduate research apprenticeship, just compressed into a single semester. And the malate dehydrogenase enzyme? Well, MDH is simply the vehicle. It provides a highly structured, manageable system for students to experience the entire research cycle. You are teaching the scientific method here, not just having them mindlessly run biochemical assays.
There are 5 core characteristics of a CURE that you really need to keep front of mind as you build out your course. First is broad relevance. You've got to explicitly show why MDH matters to things like metabolism, disease, or evolution. Second, hypothesis development. Students have to explore a question with a truly unknown answer. We're not just confirming what we already know. Third, engaging in scientific practice, meaning they are scientists asking real questions, not just texts following a recipe. Fourth is collaboration, because science doesn't happen in a vacuum. And fifth, maybe the most important, iteration. You absolutely have to leave room in your timeline for mistakes and redos. That's just the reality of building scientific knowledge.
Moving on to Section 2, choosing your project theme and framing the experimental focus.
So early on, you have to decide how you're going to frame the research. For folks in the 2026 MCC cohort, you're likely choosing between 2 specific tracks. Option 1 is drug discovery, which is tailored specifically for general chemistry. Option 2 focuses on the phosphorylation of the C-tail of MDH. This one is super versatile and can be adapted for pretty much any level course. But keep in mind, the community is always evolving. If your background is in physiology or genetics, those are great areas for growth too. Just pick the theme that aligns best with your expertise and your specific timelines.
Next up is Section 3, Structuring Your Syllabus Flow, the rigid backbone of backwards planning.
Before you even start plotting out your weekly schedule, take a step back and ask, are you in a lab or a lecture? What level are your students? Your specific environment entirely dictates how your students are going to dig into the primary literature and computational tools to find that knowledge gap. This is the crucial step where they find the what if that transforms a canned exercise into authentic research.
Regardless of the theme you choose, every MDH CURE syllabus has a non-negotiable sequential flow. This is your structural spine. It goes scientific background, leading straight into hypothesis development, moving to proposal creation, then the actual experiments, and capping off with analysis and communication. You can tweak a lot of things in your course, but this specific sequence, anchored by discovering the unknown, is the true backbone of your calendar. Once that flow is set, you hit a practical logistical choice: make versus borrow. Will your students create brand new mutants from scratch, or will you use existing ones? A lot of instructors have students design and express completely new mutants. Others prefer to borrow existing ones that already have some preliminary data, kind of like inheriting a grad student's project and picking up where they left off. But here's the kicker. Even if you hand them preliminary data to save time, you can't just hand them the hypothesis. They still need to formulate their own hypothesis from that inherited data.
Section 4. Building with required modules, the core architecture of your semester.
Think of your syllabus as inherently modular. There are required modules that form the baseline of your calendar. First, hypothesis development. This usually takes about 3 to 4 sessions, and you can use structural biology mini-reviews to get students up to speed on the enzymology. Next is expression, purification, and characterization. Figure on 2 sessions using BL21/PET28A plasmids. Then the core hypothesis testing and experiment phase, taking another 2 to 4 sessions. Finally, communication and presentation. That's usually just 1 session, often wrapping up during finals with a poster or a paper.
Now time for a collegial reality check on time constraints.
If you're working with the standard 3 to 4 hour weekly lab, expect your kinetics work to land right around specific activity, maybe touching on some regulation. Squeezing in a full Michaelis-Menten analysis? That is incredibly tight. It's not impossible, but it's tough. So give yourself some grace here. You really don't have to fit everything in. Find the balance that practically works for your course logistics.
Which leads us perfectly into Section 5, selecting optional modules, scaling up, and customizing your cure.
Once you've established your required core, you can start scaling and customizing by sprinkling in these optional modules. Maybe you add sessions on molecular visualization using MolStar or PyMol. Or you could do sequence variation predictions with AlphaFold 3. You can explore docking with SwissDoc or dive into site-directed mutagenesis PCR. The beauty here is that if you lean on computational tools and existing mutants early in the semester, it can free up super valuable lab time for much deeper biophysical or kinetic experiments later on.
All right, our final section, Section 6, assessing the scientific process, grading what actually matters.
Assessment in a cure simply has to look different than a standard course. Authentic research is inherently uncertain, so you really want to grade the process, not just the product. Take a look at this suggested weighting. Scientific background is at 10%. Hypothesis and proposal, 15%. Experimental design, which relies heavily on troubleshooting and technical competency, is a solid 20%. The lab notebook gets 15%. Data analysis is 15%. Communication is 15%, and collaboration rounds it out at 10%. You are explicitly rewarding the development of critical thinking and scientific skills, not just a successful day in the lab.
Notice how the actual gritty process of doing science makes up the majority of the overall grade. Your rubrics are basically split into 4 main chunks: research foundations at 25%, conducting research at 35%, scientific communication at 25%, and data analysis at 15%. Look, when a student's experiment inevitably fails because, let's be honest, real science fails sometimes, their grade shouldn't just tank. Not if their troubleshooting, notebook documentation, and evidence-based conclusions were rock solid.
To push your assessment even further, you might want to look into these optional grading enhancements. Skills badging is a great one. Students earn competency badges for things like accurate pipetting or running an SDS page. It assesses lab skills totally independent of their experimental outcomes. Or you could try specifications grading. Here, students have to meet established criteria on, say, a notebook check. If they don't, they revise and resubmit until they hit those expectations. These are fantastic tools for fostering true iteration and technical mastery. As we wrap up this blueprint, I want to leave you with a really supportive piece of advice straight from the source material. First time, make it simple and give yourself grace. Designing this syllabus is a big undertaking. Please, don't try to cram in every single optional module. Start with that required backbone, keep things manageable, and be kind to yourself as you step into the role of a research mentor in your classroom.
And that brings us to our final thought for you to chew on. As you finalize your syllabus blueprint, how will you ensure your students truly experience the authentic, sometimes messy, uncertainty of real scientific discovery? Remember, the end goal here isn't a perfect gel. It's empowering them to become real scientists. Embrace the unknown, lean heavily on the MDH CURE community, and get ready to design a highly effective semester. Thanks for joining me on this explainer.